Good morning, good afternoon, or good evening. Welcome back to Unit 5, Circular Motion for Honors Physics. Today, guys, we will be reviewing Lesson 5.2, Rotational Dynamics. This is for the benefit of anyone who maybe missed this lesson the first time we presented it in class, or who would just like to review the material. Before we jump into it, let's take a quick moment to talk about Newton's laws of motion, specifically Newton's first law. Now, we already discussed Newton's first law of motion in a previous chapter. It is a law that says that if you want to change an object's velocity, you must apply an unbalanced force. That is, there must be a net force that is not zero. So if you want an object to speed up, slow down, or change directions, there must be an unbalanced force. Well, the same is true for rotation. If you wish for an object to spin faster or spin slower, then you must apply an unbalanced force. The effectiveness of this force depends on a couple of factors. First of all, it depends on how far you apply the force from the axis of rotation. The further out the force is applied, the more effective it will be in changing the object's rotation. That's why if you have a nut that is stuck on a bolt and you're trying to get it loose, it's much easier if you use a wrench with a really long handle than a wrench with a short handle. The second factor that influences how effectively a force can change an object's rotation is the distribution of mass in the object. We call that the moment of inertia, and we will talk about that in more detail in just a couple of minutes. So first of all, let's address the concept of lever arm. A lever arm is kind of an abstract concept. It's not a real distance. It is the effective distance at which a force is being applied to cause rotation. To find the lever arm, you extend a line of force until the radius of rotation is perpendicular. And I realize that's a very hard concept to visualize. So we're going to take a look at some diagrams, illustrations, and maybe it'll make a little bit more sense. Let's start with something pretty straightforward. Here we have a wrench, and a force is being applied at a distance of 0.2 meters or 20 centimeters from the axis of rotation. So we will call this the radius of rotation. That's 0.20 centimeters. The force is being applied exactly perpendicular to the radius, so the angle that we're interested in is 90 degrees. To calculate the lever arm, or the effective distance over which this force is being applied, we multiply the radius by sine theta, where theta is 90 degrees. Well, the sine of 90 degrees is equal to 1, so this boils down to just 0.20 meters times 1, and the lever arm is exactly the same length as the radius. This is the most effective way you can apply a force to cause an object to rotate, at 90 degrees to the radius of rotation. Alright, but what happens if the force is not being applied at an angle of 90 degrees? In this situation, the force is being applied at an angle of 30 degrees to the perpendicular, or 60 degrees to the radius of rotation. And it's that 60-degree angle is actually the one that we're going to be concerned about. So here's what we're going to do. We want to find the lever arm, the effective distance at which the force is being applied. We're going to extend this line of force. We're going to extend it backwards. And as we do so, we're going to take this radius and we're going to rotate it until it is exactly perpendicular to the line of force. So take a look. So there we go. Once this radius becomes perpendicular to the line of force, then its length is the lever arm. Now, it's important to point out that this doesn't represent a real distance. There's nothing in this setup that is exactly equal in length to this lever arm. It's more like an effective distance. It gives us an indication of how effective this force will be in causing the wrench to rotate. All right, so the angle of interest is 60 degrees. There it is. And we will find the lever arm by multiplying the radius, which is still 0.20 meters, by the sine of 60 degrees. 0.20 meters times sine of 60 is about 0.17 meters. So we see that the lever arm in this case is less than the length of the radius, which tells us that applying the force at this angle will be less effective than if we had just applied it perpendicular to the radius. So if we change the angle between the force and the radius, then it becomes less effective at causing the wrench to rotate. Let's move on. All right, so here's another situation. This time the force is being applied at an angle of 45 degrees with respect to the perpendicular. We wish to find the length of the lever arm. Now if we extend the force backwards in this direction, the radius, as we sweep it out to meet the lever arm, will just get longer and longer and longer, and the angle between them will get smaller and smaller and smaller. So that's not going to work. We want to actually extend the line of force in this direction so that the lever arm will eventually intersect the line of force at a 90-degree angle. Now, if this is a 45-degree angle, then this angle over here is also 45 degrees, which means that the angle between the line of force and the radius is also 45 degrees, and that's the angle that we're going to be interested in. So to calculate the lever arm, we're going to take the radius, which is still 0.20 meters, multiplied by the sine of 45 degrees, and get 0.14 meters. Again, applying a force at 45 degrees makes the lever arm much shorter than the radius, which indicates that this force will be less effective at causing the wrench to rotate. The most effective force is a perpendicular force. So here we have a situation. We have a door where a force is being applied to the doorknob at 3 different directions, and we are asked to calculate the lever arm for each applied force. So I'm just going to go ahead and copy this, and we'll move it over to another page so we have a little more room to work. Maybe. All right, let's take a look at this first situation. The lever arm, or the force is being applied at an angle of 90 degrees with respect to the door, with radius being just the width of the door. It's terrible. Okay. The radius is the width of the door, and the force is being applied at a 90-degree angle. All right, so in this case, we can say that the lever arm is equal to the radius times the sine theta. Well, of course, the radius is 0.90, which is the width of the door, the distance from the hinge to the doorknob, and theta is 90 degrees. And the sine of 90 degrees is 1. So the lever arm is equal to the width of the door, 0.90 meters. Okay, so that's pretty easy. But let's take a look at this next situation. All right, here we have a force that's being applied at an angle of 30 degrees to the perpendicular. Again, remember, this is the radius here. We'll use these line tools, semi-line, much neater. And we are going to extend the line of force, extend it backwards, such that rotate the radius outward, it intersects the line of force at an angle of 90 degrees. That looks like it might be about 90 degrees, so we'll call it good. Right? And so the length of that line right there is the lever arm. Now the angle that we want is not 30 degrees. That's the angle with respect to the perpendicular. We want the angle with respect to the radius. Well, that's easy enough to figure out. If the angle with respect to the perpendicular is 30 degrees, then this angle must be 60 degrees, because perpendicular is 90 degrees and 30 plus 60 is 90 degrees. All right, so the lever arm for this situation is equal to radius times the sine of theta. Radius is still 0.90 meters, as always, for this situation. And the sine in this case is 60 degrees. All right, so you want to grab your trusty calculator and punch that in. 0.90 meters times the sine of 60 degrees is approximately 0.78 meters. The lever arm is shorter than the radius, which means that this force will be less effective at causing the door to turn, which is not surprising because it's not being applied perpendicular. All right, one more example. As before, we're going to extend this line of force out. Now this time, draw my radius here. This time, we're going to extend the force in this direction, because if we extend the force in this direction, and we continue to turn this radius outwards, you can see that the angle between the radius and the force is just going to get smaller and smaller and smaller. We don't want that. We want the radius to meet the force at a 90-degree angle. So we are going to extend this line of force backwards. So I have to go too far because this isn't a huge angle here. And so the radius meets the line of force at a 90-degree angle. That looks about right. It's fine. It doesn't have to be precise. We're not drawing a blueprint. All right, we'll call that a 90-degree angle. And let's see if we can figure out, so the angle that we're interested in is this angle right here. And if we sort of extend this perpendicular line back here, if this is 10 degrees, then this is also 10 degrees, which means that the angle that we're interested in, this angle right here, must be 80 degrees, because 10 plus 80 is 90. Right, so the length is equal to the radius times sine theta as usual, as it always has been. The radius is 0.90 meters as usual, and the sine in this case is 80 degrees. Now the sine of 80 degrees is not 1, but it's pretty close to 1, which means we expect that the lever arm is going to be very close to 0.90 meters. And in fact, when you punch it into your trusty calculator, you find that it is actually 0.89 meters, which is very close to 0.9. And that's to be expected when the angle is very, very close to perpendicular. All right. So the next concept that we want to talk about is torque. Torque is represented by the Greek letter tau. And for some reason, when I converted this back to the font that I was using for the rest of the presentation, it made that tau look like just a capital T. Okay, but in reality, tau is going to look like this. It's going to be a little crossbar and then a little twist. Okay, so the Greek letter tau looks more like that. Okay, so just keep that in mind. I didn't even notice that it had changed that back to a normal T. All right, to find the torque, you multiply the applied force by the lever arm. So remember, the lever arm is equal to R times sine theta. The torque is a measure of how effectively this force is going to cause the object's rotation to change. So the bigger the torque, the more effective the applied force will be at changing the rotation of the object. So here we have 3 wrenches that are being used to turn a nut. The most effective force is going to be at a perpendicular angle at a long distance from the axis of rotation. If we apply the force at any angle other than perpendicular, it is actually going to reduce the effective torque, which will make it harder to achieve the task that we're trying to do. Also, if we move the applied force closer to the axis of rotation, that will also reduce the effective torque because it decreases this value R, which again will make the job harder. It'll make it harder to change the nut's rotation. The SI unit for torque is going to be a Newton times a meter, and we usually just say Newton meters. All right, so here we have a skill practice problem. It says Alex is pushing down on the end of a crowbar that is 0.60 meters long. So that's the distance from the pivot point to the point where Alex is applying a force. If Alex applies a force of 300 newtons at an angle of 20 degrees with the perpendicular, how much torque is Alex applying to the crowbar? I'm going to neglect the mass of the crowbar itself because in reality, the mass of the crowbar has weight, and that would also apply a little bit of extra torque. So if we had to account for that, it would just make the problem that much more complicated. So we're going to copy this problem. We will add it to a new page just to give us a little bit more space to work. Let's see what we got. All right, first things first, the formula for torque. Torque is equal to the applied force multiplied by the lever arm, or the applied force multiplied by the radius of rotation multiplied by the sine of the angle theta. So we'll start out by figuring out what is this angle theta. Well, it's not 20 degrees. Okay, that's kind of a misleading bit of information. 20 degrees is the angle between the perpendicular and the radius, and we'll just draw a red line here to represent this radius. Boom, there it is. Okay, the actual angle that we're interested in is going to be this angle here. Okay, well, that's easy enough. If this is perpendicular, then the sum of these two angles is 90 degrees. This is 20, so this must be 70 degrees. So that's the actual angle that we want to use. Theta is equal to 70 degrees. The radius is 0.60 meters, and the applied force is 300 newtons. We have all the information we need now to solve this problem. So we're going to say tau is equal to the applied force, which is 300 newtons, multiplied by the radius, which is 0.60 meters, multiplied by the sine of the relevant angle, which is 70 degrees. And you pull out your trusty calculator and multiply those three things together. Round your answer down to two significant figures, and you're going to get 1.7 times 10 to the second power Newton meters. Or you could write 170 without a decimal point, and that would also be fine. Anyway, that's going to be our final answer. So put a box around it. Whatever you want to call this shape. Sometimes there's more than one torque being applied to an object, just as there can be more than one force applied to an object that is moving in a linear direction. And just as multiple forces can combine to produce a net force, multiple torques can combine to produce a net torque. If the net torque is zero, then an object is not experiencing any angular acceleration. In other words, its rotation rate is not changing. So here we have another problem. Let's take a look at this. Alice, who weighs 400 newtons, and Brianna, who weighs 360 newtons, are sitting on a seesaw. Alice is sitting 1.50 meters from the fulcrum. How far from the fulcrum must Brianna sit to balance Alice? And again, we are ignoring the mass of the seesaw. So let's copy this problem. Paste it onto a new page. Alright, so I'm just going to sketch a diagram. I realized I had a diagram on the other page, but I'm going to sketch one that's a little bit more helpful. Okay, so this is going to be our seesaw. And we will draw the pivot point, or the fulcrum, right here. Okay, and Alice and Brianna, they're just going to be circles for this problem. So we'll put Alice right here, and we will label that circle A for Alice. And the direction, or excuse me, the distance, I should say, between Alice and the fulcrum, I call that distance RA. R for radius, A for Alice. Right? And then Brianna is going to sit over here. We'll label that circle B. And the distance between Brianna and the axis of rotation, RB. And RB is actually what we want to find. That's the bit of information that we need to find. All right. Alice and Brianna are both applying a torque to the seesaw. Alice is sitting on this side and gravity's pulling her down, so she is applying a torque like this. Call that tau A. Brianna, who is sitting on the opposite side, is applying a torque in this direction, so we will call that tau B. Remember from our previous lesson that rotation in an anti-clockwise direction is considered to be positive, and rotation in a clockwise direction is considered to be negative. So we will assign tau A to be positive, and tau B will be negative. So we can write ourselves a net torque equation. We can say that the net torque being applied to the seesaw is equal to tau A, which is positive, minus tau B. We have to say minus tau B because tau B is negative. Now, if the seesaw is balanced, which the problem indicates that it is, then the net torque must be 0 Newton meters. So we can say 0 Newton meters is equal to tau A minus tau B. We can add tau B to both sides, and because we have 0 over here, then we're just going to get tau B is equal to tau A. Now the formula for tau, for torque, is force times radius times sine theta. In this case, both girls' weight is being applied exactly perpendicular to the length of the seesaw. So theta in both cases is going to be 90 degrees, which means that sine of theta is going to be 1. So we can actually just leave that out for this problem. So we'll say that torque of B is equal to the radius of B, which is the thing we're trying to find, multiplied by the force of B. And we could put that the other way around, but it doesn't really matter. Where torque of A, tau A, is equal to radius A multiplied by force A. And we know all of this information except for RB, which is, again, what we're trying to solve for. So force of B, that's just Brianna's weight. That's 360 newtons. So 60 newtons. R of A, that's the distance that Alice is sitting from the fulcrum, and that's 1.50 meters. And force A, that's Alice's weight, that's 400 newtons. All right, so we multiply these two numbers together, that's going to give us 600. So we have RB times 360 newtons equals 600 newtons times meters. And then we divide both sides by 360. And punching those into your trusty calculator, 600 divided by 360 is going to be 1.6 repeating. We will round that to 3 significant figures, and we find that Brianna must sit 1.67 meters from the fulcrum in order to balance Alice. And that's our final answer. All right, another similar problem. Brian is making a mobile hanger for his baby brother's crib. What mass must Brian hang from the free end if he wants it to balance horizontally? So this is very similar to the seesaw problem. We're going to employ a similar approach to solving it. First of all, let's define the torques that exist in this system. All right, so the mass, this 0.25 kilogram mass, is exerting a torque like this. And we'll go ahead and label this mass A just to have something to call it. So we will call this tau A. And then this mass over here, which, why not, we'll call it B, is exerting a torque like this. It wants the whole mobile to spin this direction. So we'll call that tau B. And since anti-clockwise is positive, we will let tau A be positive, tau B negative. Now we want this mobile to balance, which means that the net torque is 0. So the net torque is equal to tau A minus tau B. We're calling tau B negative because it will cause the mobile to rotate in the clockwise direction. The net torque is 0 Newton meters. We'll add tau B to both sides, so we get that tau B is equal to tau A. All right, tau B is equal to force B multiplied by radius B. And we could put in sine theta B, but again, if this is balancing horizontally and this mass is pulling straight down, then the angle here is perpendicular, which means that theta is 90 degrees, sine of 90 degrees is 1, so we can just leave it out. Is equal to force A multiplied by radius A. The force B will be equal to the mass of B multiplied by gravity. So we can say mB times G times RB. And the force of A is going to be equal to the weight of A, which is the mass of A times gravity. So MA times G times RA. Now you notice that gravity appears on both sides of the equation, which means we can actually cancel it out. It's not going to affect our answer. And now we plug in the information that we already know. Do not know the mass of B, so let's leave that out. We do know that the radius of B is 0.50 meters. We know that the mass of A is 0.25 kilograms. And the radius of A is 0.20 meters. All right, simplifying that right-hand side, we're going to multiply 0.25 times 0.20. And that is going to give us, we'll do this up here, 0.25 times 0.20 is going to give us 0.050 kilograms times meters. So what's a kilogram meter? I don't know, it doesn't matter. It's just an intermediate unit that we're getting on the road to solving this problem. On the other hand, we still have MB times 0.50 meters. So to finish up, we're going to divide both sides by 0.50, and we're going to get MB is equal to 0.10. Meters are going to cancel out, so we're left with kilograms. So the mass of the object hanging on the right-hand side must be 0.10 kilograms, or 100 grams, in order to balance this mobile. That's our final answer. All right, so now we're going to talk about moment of inertia. Moment of inertia is to rotation as mass is to linear acceleration. In other words, it's you can think of it as the resistance to a change in rotation. It is largely dependent on how the mass in an object is distributed. So the more the mass is distributed towards the center of rotation, the smaller the moment of inertia will be, and the less the object will resist changes to rotating. The more the mass is distributed towards the outer rim, the greater the moment of inertia, and the more the object will resist changes to its rotation. Moment of inertia is measured in kilograms times meters squared. So here's a chart that illustrates the formula of moment of inertia for various shapes. And you can see that the shape of the object greatly affects how the moment of inertia works. For a thin hoop, that is where all the mass is concentrated in the outer rim, the moment of inertia is just the mass times the radius squared. And that's the simplest formula. And then as we get different shapes with different moments of inertia, we get different formulas. This cheat sheet is available in the the skill practice problems worksheet that I uploaded to Google Classroom. So take a look at that. Have that handy as you're solving some of these problems. So here we have two wheels. In this wheel, the mass is distributed more or less evenly throughout the body of the wheel. In this wheel, the mass is concentrated strongly in the rim. If both wheels have the same mass and outer radius, then the question is which wheel would have the greater moment of inertia? And we would suspect that this wheel would have the greater moment of inertia because its mass is concentrated further from the radius. So if we apply the same torque to both wheels, this wheel will spin up more slowly and this wheel will spin up more quickly. All right. Copy this problem. This problem is going to take quite a bit of space to work out, so we'll go ahead and move it over to a fresh page. There we go. All right, so it says a twirling baton is a thin uniform rod with two rubber caps at each end. The rod is 0.60 meters long and has a mass of 0.10 kilograms. The caps are small enough to be treated as point masses, which are 0.15 kilograms each. Determine the baton's moment of inertia as it is rotated about the midpoint, so here, and around one end. All right, this is a really involved problem, so we'll go ahead and jump into it. First, we'll focus on this situation where the baton is rotating around its midpoint, right? we will say that the moment of inertia, we'll call this I total, is going to be equal to the moment of inertia of the rod plus the moment of inertia of each end cap. It's cap A, cap B. Now, because the end caps have the same mass and they are the same distance from this axis of rotation, their moments of inertia should be the same. So we can simplify this just a little bit by saying that I total is equal to moment of inertia of the rod plus 2 times the moment of inertia of the end caps. So now we just need to get formulas for these and we're good to go. Well, looking at our cheat sheet, moment of inertia of a rod that is rotating around its central point is given by 1/12 the mass times the length of the rod squared. All right, so we're just substituting that in for I rod. And because we are treating the end caps as point masses, their moment of inertia is given by mass times radius squared. All right, so we basically have all the information that we need to solve this problem. It's just a matter of plugging it all in and entering in the calculator. So I total is equal to 1/12 times the mass of the rod. The mass of the rod was told to be 0.10 kilograms, times the length of the rod, which is 0.60 meters, and then we must square that, plus 2 times the mass of the end caps. Each end cap is 0.15 kilograms, multiplied by the radius of rotation. If the rod is 0.60 meters long and it is spinning around its midpoint, the radius of rotation is 0.0 meters. And we should square that. Okay, that's a lot of numbers there, but if you punch them all carefully into your trusty calculator, you will find that the total moment of inertia for this setup right here is going to be 0.030, we get 2 sig figs, kilograms times meters squared. Okay, so that's the first part of the problem. Now, we're going to consider what happens when we spin the rod around an endpoint. Okay, so we'll say that I total is equal to the moment of inertia of the rod plus, okay, we don't have to consider both end caps because one of the end caps is in the middle here and we're treating it as a point mass, so it's not really doing anything, it's just sitting there. So we only need to focus on this one way out here that's swinging around the midpoint. All right, so we will just have the moment of inertia of one end cap. This time we are not spinning the rod around the midpoint, we're spinning it around one of its endpoints, so we have to use a different formula. It's not 1/12 mass times length squared, it is 1/3 mass times length squared. Again, if you consult your cheat sheet, you'll see how this works. Plus, the end cap is a point mass, so it is m times r squared. Plug in the numbers that we know. Mass of the rod is 0.6, no it's not, excuse me. Mass of the rod is 0.10 kilograms, multiplied by the length of the rod, which is 0.60 meters squared. The mass of the end cap is 0.15 kilograms. And the radius of rotation, since it is swinging around the entire length of the rod, the radius of rotation this time is going to be 0.60 meters, and then we have to square that. So you punch all this in and hit enter, and your calculator will tell you that the moment of inertia for this system is 0.066 kilograms times meters squared. All right, so you can see that in this situation, the moment of inertia is actually greater than it was in the previous situation. So it's actually harder to get the baton spinning up when you're spinning it around one end than it is when you're spinning it at the middle. So it does matter how the mass is distributed with respect to the axis of rotation. We were talking about Newton's laws of motion earlier. Now let's focus on Newton's second law. There is a rotational analog of Newton's second law, which says that the acceleration of an object is proportional to the net force, but inversely proportional to the object's mass. Well, in terms of rotation, the angular acceleration of an object is proportional to the net torque that is being applied to the object, but inversely proportional to the moment of inertia. So let's take a look at how we can apply Newton's second law of motion to rotation. We have a solid steel wheel with a mass of 15 kilograms and a diameter of 0.44 meters. Let's pay attention, that's the diameter, not the radius. We want to make this wheel rotate at 8.0 revolutions per second in 15 seconds. So we want to know, first of all, what torque must be applied to this wheel. And secondly, how much force, if we wrap a strap around the wheel and pull on the strap to make the wheel spin, how much force are we going to have to apply to that wheel? All right. We'll start with the rotational analog of Newton's second law of motion. Which is that the angular acceleration, or alpha, is equal to net torque divided by the moment of inertia. The moment of inertia for a solid wheel, you can find that from our cheat sheet, is given by I is equal to mass times radius squared. No, it's not. Is equal to I times 1/2 mass times radius squared. The mass of the wheel is given to be 15 kilograms, and the radius of the wheel is half of the diameter. So if the diameter is 0.44 meters, then the radius is 0.22 meters, and we must square that. All right, so if we take 1/2 of 15 times 0.22 squared, we find that the wheel's moment of inertia is 0.36 kilograms meters squared. All right, so we're going to save that number because we're going to need it for use later. But that is the number that goes right there. All right, next let's see if we can find the wheel's angular acceleration. The angular acceleration, if you remember from the review of lesson 5.1, is equal to the wheel's final angular velocity minus its initial angular velocity, all divided by the time that it took to spin up. The initial angular velocity, since the wheel is assumingly starting from rest, the initial angular velocity is 0 radians per second. So we just need to figure out what the final angular velocity is. And we're told that it's going to spin up to 8 revolutions per second. So we want to change that to radians per second. All right, so the omega F is equal to 8.0 revolutions per second. We're going to bring revolutions to the bottom, and we're going to put radians on top. We know that 1 revolution is equal to 2 pi radians. So we're going to say 8.0 multiplied by 2 pi over 1. And revolutions will cancel out, and we'll be left with radians per second. 8.0 times 2 pi over 1, when we do that multiplication and then round it down to 2 significant figures, gives us 50 radians per second. All right, So the angular acceleration is going to be equal to 50 radians per second minus 0 radians per second, all divided by the time that it takes to spin up, which is 15 seconds. And 50 minus 0 is, of course, just 50. So we have 50 divided by 15, which is, to two significant figures, 3.3 radians per second squared. All right, so we have the moment of inertia, we have the angular acceleration, we can work out the net torque. Say that 3.3 radians per second squared is equal to tau net divided by 0.36 kilograms meters squared. So we're going to multiply both sides by 0.36, and we're going to find out that the net torque, which is what we're searching for, this first part of the problem, is equal to 1.2 newtons times meters. So hooray, there's the answer to the first part of the problem. The second part, fortunately, pretty simple. This force is applying a net torque of 1.2 meters. Okay, so we know that tau is equal to force times radius times sine theta. Well, in this case, the force is being applied at a 90-degree angle to the radius of rotation. So sine theta is just going to be equal to 1. So we can ignore that. Say 1.2 Newton meters is equal to the force multiplied by the radius, which is the radius of the wheel, at 0.22 meters. Divide both sides by 0.22 meters, and we find that the applied force must be equal to 5.5 newtons. So that's it, folks. That's lesson 5.2. Our next lesson, 5.3, we will get into the concept of rotational equilibrium. That'll be new material for everybody. Nobody has seen that yet. So we will probably get into that after spring break. I appreciate your time and attention. I would ask you to please go over to Google Classroom. There will be a Google form in addition to this, a link to this PowerPoint on YouTube. And I would ask you to complete that Google form. And if you have any questions, to please post them there. Thanks for your attention. Have a great day. Stay safe.